and start the time. Yeah, okay. No, we can just leave it open for now. It's not too... okay, all right. So welcome everybody to the presentation. Today we're going to be talking about machine learning in the concepts of computer vision. How does a computer see, and how can we train it to see what we want? So first we'll talk about what is actually computer vision, what are the common problems that we experience, what the kind of things that we can do. How can we how can we process images? How can we make the computer understand what an image is? Where, for example, in an image, where the edges are, where how to extract like features, because we maybe want to say whether an image contains a cat. Well, we're gonna see how we can actually do that. Then we're gonna talk how does those basic concepts actually translate into convolutional neural networks, because while they might seem difficult to understand first, they're made up of just a few very simple concepts that are working together in a certain way. Then we'll talk about autoencoders, which concern themselves with how the computer represents the data, so that it basically summarizes whatever you give him, because you might not need, for example, for an image, you might not need all of the pixels in the image to recognize it, to reconstruct it, to maybe draw it. For example, a human can draw an image just based on information. You don't need like a reference image to do it. And then we're gonna talk about the advancements in autoencoders, the variational autoencoders, and how they work and what they do. And so each concept will have the intuition behind it explained. Okay? So we start with the basic task of computer vision. What are we looking at, guys? We can have just a simple placeholder image on the left. It contains some mountains, it contains a sun. Well, we would like to classify that. Why would we do that? Well, for example, let's say Google, right? Let's say that you want to look at the picture of cats. Well, Google can search through the whole internet. It can trust the users to label their pictures explicitly as containing cat, but you have a problem, right? You can't really trust users. They can label something like a cat that you don't want to see, that they can label a dog, and can be very, very confusing. So what you would rather have to do is like have an artificial intelligence that can look at the picture and is like, hey, that's a cat, you know? Like if we're gonna be asked about cats, we can give it, you know? Like we don't trust the users because we just trust ourselves. So, well, okay. So how can we do that? Because we need to look at the picture and we need to translate basically all of the numbers, all of the pixels in the picture into just a single number, basically telling us what it is, right? So this is just a simple fully connected neural network, and we're gonna see how we can use it in its simplest form. So the fully connected network, the way it works, very simple. You have some input data. In this case, this could be pixels. So one could be a very intense pixel. Think about grayscale image. One is white. 0 is black. Right, so we have, in this case, we have a very simple image of just 4 pixels. And we would like to put it into a fully connected neural network, which has weights, which has numbers. It basically says, okay, how important are those pixels? What can we learn from them? How can we define the relations between the pixels that we've inputted and the numbers that we output? And the numbers that we output are actually just classes. So in this case, you can say, okay, this is a simple machine learning problem. We input images, and we want to see whether an image contains a boat, a car, or a plane. So if you could just imagine that on the right here, the 0.96, it could be the probability that the 96% that there's a car in the picture, right? So there would be, for example, a 4% probability that there's a plane, so very unlikely, but like a 32% probability maybe there's a boat, you know? But we are pretty certain it's not a boat, it's a car. So let's try to actually use that, right? Let's try to input those images. So we can look just like a very pixelized version of my selfie, where you can clearly see the image, right? You can clearly see the counters. You can see the edges. You could make out my eyes, my face, my mouth. You could see that it's me. And well, but what does the computer see? Well, while we see the actual edges, we see the actual parts of a human face, the computer just sees numbers, right? It's a lot easier to recognize me from the picture on the left than from the picture on the right. and then the picture in the middle just shows both of those things. Okay, but let's say that, well, we just use the fully connected network and we give it the picture. What's going to happen? Well, the fully connected network, it just expects a string of numbers, right? So what we would have to do to actually input the image into a fully connected network, we would have to put all those numbers right behind each other. Well, you might say that a computer might maybe understand it at some point, but we're kind of missing some things. Wait. Yeah, so, yeah, hi Lara and Emma. Hi, join us. We're just discussing what the images are. Yeah, so in this case, we have a 28 by 28 pixel image that we translate into numbers, and we basically have a string of 784 numbers in total that we input into the computer. That's difficult, right? Because, well, what we might have had is, for example, in this case, a picture of a tree, and you yourself, guys, you can actually recognize what the picture of a tree is, right? You see different shapes, you see different positions of those pixels. But what we now input in the computer is a simple string of numbers. So you can see that the black blocks on the left are actually from the frame of the picture, right? Like the top frame is here on the left, the left and the right pixels are here represented here, and then, well, you have the actual top of the tree starts here, right? And you can imagine this as a kind of string, right? Well, while you could recognize from this picture that this is indeed a tree, if I give you this picture, you won't be able to see anything. Why? Well, that's because by just treating every number the same, we lost some very important information. We lost the spatial information of where the things are positioned. It's very now difficult to see, and we lost the shapes. It's very easy for you to see from a simple picture where's the circle, where's the square, but from this picture, you won't be able to see anything. You lost the shapes. And it's also a problem, right? Because that's not how humans see. This particular picture, right? Like humans look at parts of the picture. They look, okay, so where's for example, a nose? Where's an eye? Like, how can I construct a face out of it? And, well, by just inputting it into a fully connected network, we create some problems, right? First of all, we miss the shapes, we miss the coordinates of the things, but also we ignore arguably the best object recognizers that we have on our hands, the humans. You know, the science has looked for ages at nature, like seeing, okay, how do birds fly? How can we model airplanes out of that? How do ants, while being so dumb, such dumb robots, how do they build such complex structures? How do they express such behavior? So we can actually try to build the recognition model based on how the humans see it. And how do humans see it? Well, the neuroscience department, the neuroscientific department tells us that the humans actually start seeing the picture by focusing at more small shapes, right? So what they proposed maybe 30 years ago is that the human might look at first the edges of a picture, right? As you can see here on the left, it might just look at simple lines. Then from those lines, it might construct well, shapes, you know, that a face might have. For example, eyes. For example, mouths, noses, ears, and then it looks at the picture as a whole. Then it looks at actual faces, and then, well, you can recognize the faces. But even from those shapes in the middle, you can already recognize that it's a part of a face. So how can we actually do that? Well, now instead of our problem right now, instead of recognizing what a picture has, our problem has transitioned into how do we recognize the features? How do we recognize those lines? How do we construct shapes out of those lines? Well, so how can we, given those numbers, given those pixels, how can we extract actual features? For example, from these numbers, how do we extract edges? So if I wanted to represent this picture, but I didn't want any colors, any shapes, I just wanted the edges of the shapes. I didn't care about how they looked, I just cared about where they're placed. Well, turns out there is an operation. People a very long time ago have come up with what's called a Sobel operator. And the way that it works is that they first focus on a single pixel. For every pixel in the image, for example, in this case, they take the pixel 73. And then they look at which pixels surround it in the hopes of actually trying to find, well, the edges. Because you can't really find an edge of an object just by looking at one pixel. You need to look at what's around it, right? And then you can see, okay, so which edges can I find? So what they then do is that they have come up with an edge extractor. In this case, it's a Sobel operator. You don't need to know how it works, like why those numbers are there. But it's important to understand what the operation is of extracting features. So as you can see here, you have 9 pixels in total, a 3x3 matrix, and you also have a 3x3 Sobel operator. Well, that's not a coincidence, because how the algorithm works is that it first looks at one pixel and multiplies it with the same position in our edge extractor. It then does it for all the other pixels, summing them up as they go, to then come up with a single number, right? It just finds just a single number following this very simple equation, and then it creates a new picture. In this new picture, it only outputs those numbers, right? Those numbers then actually create the edges, right? So so if you apply the Sobel operator on my image, what you will get is more of the edges. You can see the clear separation between my hair, the background, between my shoulders, my neck, between the t-shirt that I have on. So this operation has a name, and this operation has a very interesting name. This is what we call a convolution operation. We used those predefined numbers to convolve, to extract some features. We basically slid this whole matrix around the whole image, focusing on each pixel individually and trying to extract data from it. Okay, so let's try to relate it to the actual simple fully connected neural network that we had, right? It just gets some input and it gets some output, right? And it multiplies and it adds it and it multiplies it. It doesn't matter, but it just gets some input and some output. That's what matters, right? And for the input, we need the input layer, the actual input. We need the weights, the numbers to sum it up with, to multiply it with, and we need the output, right? In this case, we need for every pixel to have a certain value, right? But when we use the convolution operation, we use the input, which was the neighborhood of the pixels. We actually used some weights, but those weights were not from a fully connected network. Those weights were defined by a human. And then we got some output, just a single number. So for neural network, you need the input, the weights, and output. And we just used the input, the weights, and the output. So what if we combine them? What if we use what if we use the same input, right? Those pixels, like the neighborhood around the pixels. What if we use some weights, and instead of, as you can see above, instead of the operator that people have already calculated, we instead use the neural network weights that we can train, right? So instead of trying to extract edges from a picture, we basically tell the neural network extract something from a picture, extract some features that we might use, that might be useful, and we get an output. In the first case, we got those numbers. So this is what the image becomes, like in that neighborhood after the convolution operation that you can see up top here. But yeah, let's just focus that we need 18, right? We focus on 73 and we need 18. Well, that's just a single number, so our fully convolutional, our network should only have one output, right, for that number. So let's try to extract those features. Let's simply use the pixels, the same pixels that we used in the convolutional operation to extract edges, and let's input it into our fully connected network, into a simple fully connected network that doesn't care. And then, well, hopefully we get some output. Hopefully we can find some edges. Yes. So yeah, what we used for that thing is actually a hidden layer. But a hidden layer in this case needs to be of a certain size, right? Because we saw with the edge extractor, if we focused on 3x3 part of an image, then we also needed a 3x3 matrix, a 3 by 3 weight. So what we do, okay, yeah, a 3 by 3. So in this case, if we want to focus on a 3 by 3 matrix, we would need to have 9 weights. Yeah, we would need to have 9 weights. Okay, welcome, Sommerfeld. Yes. So let's see what we have just let the network do. So the humans see by first focusing on simple lines, then going from those lines to more complex shapes, and then going to the whole image. Well, that's something that we have just done, right? We first extracted the edges, which are maybe very important features for defining what an image contains. And then we basically tell, instead of predefining what it should contain, we simply ask the network to do it for us. And convolutional neural networks is just that, right? We take a simple, fully connected network that just has some input and some output, and we, instead of putting the whole image in it at once, we instead slide it, and we slide it multiple times, right? Because in that way, we can actually create a new image which maybe contains only lines. Then we create even new image which contains the shapes that we want. For example, for recognizing a cat or recognizing a car. Maybe at some point the image contains a clear representation of how a wheel should look like, because a car should have wheels, so it makes sense to look at the wheels when you try to recognize a car. And to better understand it, we need to understand the actual parameters that you can input into the network. So the 3 main parameters of how the network can be described is the kernel size, the number of filters, and the stride size. So the kernel size simply means how big is the neighborhood that we want to look at. If we want to look at very small lines, we take a 3 by 3 neighborhood. If we want to look at bigger lines, we might take a 5 by 5 neighborhood. What it means also is that our filter, our fully connected network, also grows, because now it needs to accommodate the bigger neighborhood around it. If we increase the number of filters, then let's say that we have that extracted, which is head, right, with some predefined numbers. Now we have 2 extractors with different predefined numbers who hopefully look for different features. So you think about it, that one extractor might look for squares while the other might look for circles. So then we extract different informations from the same image, right? Because we might be interested in circles, might be interested in squares. And the stride size is an interesting one, because while both the kernel size and increasing the kernel size, increasing the filter size grows the number of parameters that you have in your network, a stride size doesn't do that. So what the stride size means is that, when you have a stride size of 1, you would first focus on 73 on this pixel, and then you would simply go on to the next one, to the 92. If you increase the stride size to 2, then instead of going from 73 to 92, you instead skip it. So basically, a stride size is just basically means how many pixels do we go further. And in this case, if we have a stride size of 2, we go from 1 pixel, you skip 1 over, and we go to the next. What this also means is that the pixel 92 is not focused on. It's still a part of other features of other pixels because we use it in the neighborhood, but it's not focused on. So we say that it's not particularly important. And one more thing that makes the convolutional network so powerful is max pooling. So, because what do we want to do? Well, we want the network to look at the image and to tell us, which pixels mean what, right? And the way that we want to do it, actually, is we want to tell the network which pixels are not what, but are the most important ones. So how can we do that? Well, a typical convolutional neural network has multiple layers, right? So first of all, for example, if you input an image, it might use those filters to focus on the original image, and then the next layer will not focus on the image, but will focus on what the previous layer has outputted, right? So how can we make sure that the first layer learns to prioritize, learns to see which pixels are the most important ones? Well, we can do it very easily. The max pool operation simply looks at the neighborhood of pixels, in this case a 2x2 matrix, and simply takes the maximum pixel from there. So in this case, if we go forward and we output and we make a mistake, we can tell the previous layer, hey, those pixels were not important. Your importance was off. You should define them better for us to find a better representation, right? So you could see that. Okay, so well, let's say that we want to classify something, that we want to maybe classify faces, right? And let's just assume that faces have a lot of horizontal lines, right? So something that's not a face might have more vertical lines. So maybe vertical lines is the thing that we're important, is the thing of importance. So by making the convolutional layer look for lines of any direction and then telling it, okay, pick the most important line direction that you thought was the most important one, we can tell the next convolutional layer to only focus on those lines. So if we do it with the max pool, the first convolutional layer says, okay, so the most important lines are the vertical lines, and here are their values. And the next convolutional layer is, okay, so let me just compare those vertical lines and see what I can do with them. And this is what convolutional neural networks are. You just slide the fully connected network across the whole image. You focus on a tiny part of it, and you focus on it by deducing multiple different parameters, features. And that's also something that, well, that's how humans see, right? Because I just said that in neuroscience, it was very popular to assume that the humans first focus on lines and edges, then they focus on eyes, nose, and ears, and then they focus on the whole face to recognize whether it's a face or not. Well, that's something that we're also doing, right? Because we are, in the first layer, we try to extract those lines, maybe. Then in the next layer, we only take the most important parameters, the most important lines, and we tried from those most important parameters to construct some features that might be important for us. So, for example, one part of the network might be tasked with recognizing eyes, while the other one might be tasked with recognizing this particular region right of a nose. And this is all that the convolutional neural networks are. Somehow the things are not updated, but that's fine. Yeah, and this is basically what the convolutional neural networks are. They simply take a very simple concept of a fully connected layer that doesn't care about the shape. It doesn't care about the position of the numbers that you input, and then it only focuses on a small part of the image, trying to find spatial relations in those very few images. Okay. Do you have any questions about what the convolutional neural networks are? So just like humans, they first look at very small parts of an image, at lines, then they focus on bigger things. Maybe when you're recognizing face, it's eyes. When you're recognizing boats, it may be the part of the boat. When you're recognizing cars, it may be a wheel and stuff like that. When you're recognizing planes, it might be wings. Do you understand how these things work? The stride size is basically tells the biggest stride size tells the network, okay, don't focus on every single pixel. You can skip some of the pixels. Of course, that's a very good question. What does the stride size do? Well, of course, if you do that, then you actually get an image which is smaller than the original image. So it might be also in a way like a max pooling operation, because you try to focus maybe first on 73 and then on 102 and on 109 in this case, and then you tell it, well, just take the most important pixel relations from this thing. Okay? Right. So now we are gonna move on to the next very cool thing, which is how do the computers actually see, and how can we make them see what they want to see? So just give me one moment. I need to. means. Learning club. Seminar. Seminars. Wait, what? Oh, I missed the thing. Okay, now. Just a moment, guys. Yeah, okay, yeah, okay. So now we can go to Autoencoders. Please go away. Right, nobody saw that. Okay. And this is mine, guys, and the rest is yours. Okay. Right. Yeah. So now I want to discuss, guys, the autoencoders. The autoencoders are a way for a computer to, well, make its own representation of data. And I want to give you guys a good intuition on why they work and why they're needed. So, well, as we have already discussed, we're again back to my selfie. The computer doesn't see the same shapes that you do. The computer just sees the numbers. It can't, at least at first, it can't see the edges, it can't recognize the eyes, the hair. So how can we use it, right? Well, first of all, you know, when we want to predict something, we usually want to minimize the amount of useless data like the fully connected network receives, right? Because if we want to recognize faces from an image, do we really need the background? Do we need their clothing? Do we need their maybe their necks? Well, not particularly, right? So some of the information is useless and some of the information can be compressed. For example, right, would you be able to recognize a face from the left picture even though I cut off the pixels around it? Well, of course, because those pixels were completely useless, right? So let me now ask you to actually extend the picture. Let's say that I give you a smaller picture and I tell you to extend it, right? Well, you probably would draw like a wall above and then on the left and on the right. And you would maybe draw my shirt that is clearly black. You would just draw it here by continuing these lines. And you would be right? Like that's something that we expect to happen. That's we don't expect those things. Of course, you don't know for 100% what's hidden in those things. It could also be that, you know, that there was a small cat hidden, you know, that there would be some, that my t-shirt would be only black at the start and then would be completely white when the image actually cut off. You make assumptions, but those assumptions do not matter because you're focusing on what's important. You're focusing on the actual faces. So again, right, in this case, we don't actually cut off anything from the image, but we make the image smaller. We make it blurrier. Can you still recognize the face? Well, yeah. So you could still, like, even if I gave you this image and I told you, okay, try to draw my face or try to tell me if I'm on the picture, you would still be able to do that, maybe with some accuracy. So even making the picture smaller didn't stop you from recognizing a face in it. So clearly, some of the data there is useless. Some of the data is redundant. You don't need 50 pixels for an eye if you can recognize it with just 10, right? So why would we have 10 pixels? Well, let me make it even more difficult for you. If I described a picture for you with just this text, I wouldn't give you a single pixel. Would you be able to know who is displayed on the picture? He has a nose and ears, brown eyes, dark hair, a mouth. He's a student at the UM, and he's standing right in front of you. It's me, guys. So you don't even really need the pixels. You just need some description, some summation of the things that you saw in the image. So how can we do that? Well, first of all, we have to understand that we have to identify faces, right? And when we're identifying faces, we have images where not all pixels are born equal. You can identify clearly, like a woman from this picture, you can identify her face, and you can identify her face as well if I cut off everything else, right? So everything that's in the gray part might be completely useless, right? Because that's not something that we focus on. So how can we teach the computer to understand what's important? Well, we can ask the computer to represent its own data, right? So learn from this data and try to summarize it, try to make it smaller. And then, well, how do we know that the summation was good? Well, use that summation to reconstruct the image. And that's something that we did before, right? Because if I cut off pixels, you can still reconstruct the image with a lot of confidence. So can we learn the computer to do the same? Can we just make it summarize the features in such a way that it stores only the most important ones, and then it uses them to predict whether this is a face or not? Turns out we can. Otherwise, we wouldn't be having this lecture. And the way that we are doing it is autoencoders. So imagine the convolutional neural networks that I've just described, but instead of a single number predicting what probability there's a face on the picture, we instead don't predict a single number, but we predict 200 numbers. And then we don't use those 200 numbers to identify what's in the image. No, we use those 200 numbers to reconstruct the image. Let's, to get a good understanding of it, let's imagine a landscape. Let's imagine some grass, let's imagine some sky. Do you need all of the pixels of the sky to try to understand that the sky is there? No, because you don't expect the sky to suddenly change into grass vertically. So some of the information in the pictures are redundant. Some information we don't need. And well, what we would love to do is for the autoencoder to take my image, to summarize it in some features. Okay, so there's a nose, there's a mouth, there's wherever he's doing the EM. That's a bit of maybe a privacy problem if he can understand that. But yeah, and then we wanted to reconstruct the image, because if he can reconstruct a perfect image from those features, that means that he only saved the most important information. The rest of the information was simply useless. And well, what if we try to summarize handwritten digits? Let's try to summarize maybe, okay, so first of all, which digits look like each other, right? So does an 8 look more like a 1 in this case, or does it look more like a 9? Well, clearly we would say that an 8 looks more like a 9 because it has a circle, it has also this part of it, this curly leg here is kind of similar to the curly leg here, maybe sometimes. But of course, it doesn't look anything like 1, right? 1 is just like a straight line. Okay, so the first thing that we can recognize is that if we had just 2 features, the x and the y axis, then these images would be placed into, they would have different values. So we would expect the 8 and the 9 to have very similar values and be very close to each other because, well, they're almost the same. But 1 is, of course, doesn't have any circles. It has very few round lines. So it's different. It's different for us. So yeah. So what the autoencoders do is that instead of using the whole image to recognize the digits in it, they instead use the most important parts of the image that they use to reconstruct it to then predict the digits. So what does it make? So why is it more important? Well, let's say that we have a 28 by 28 image, right? That gives us already almost 800 pixels. So those are 800 digits that we have to input into the network. Well, let's say that we actually can efficiently summarize it in only 100 digits. Maybe we don't need, to reconstruct a digit. Maybe we don't need the corners. Maybe we don't need anything else. We just need the middle, right? So we can already automatically cut them out. So instead of inputting into the network, we make it easier for the artificial intelligence, because instead of trying to deal with 800 digits, it now only has to deal with 100. With 100, the most important digits, because the other 700 apparently were not as important as they should have been. And well, of course, yeah. As I said, if we had some space where the images would be expressed, we would expect the 8 and the 9 to be close to each other, and the 1 to be far, right? But also, in here, we would kind of expect more ones, right? Maybe like somewhere here, there's a 1 that's more straight, or maybe somewhere here, there's a 1 that's tilted into this direction, into the opposite direction instead of 1, but still a 1, right? So we still recognize it as a 1. So actually, are those ones different? Is the 1 that's tilted into this direction actually different from the one tilted into this direction? No, they're both one, but the pixels in the image are just different. So we could. So what people have thought about it, people have thought, and they have come up with variational autoencoders, and instead of just summing it into digits, the variational autoencoders actually kind of create spaces in here. They basically say that that if I have a 1, it's probably gonna fit somewhere here, because I don't care if it's tilted this way, if it's completely straight, wherever, it's gonna be fit in somewhere here. You also don't care how big the two circles in an 8 are. You know, like you expect it to be somewhere here, right? Yeah. So, and then, you know, maybe there's some noise, maybe you took a picture wrong, and maybe there are some more pixels here, right? So there's actually kind of a chance, right? There's a chance of a noise. There's a chance that the pixels will be in a certain position given a 1, right? So if we have a 1, the pixels might be slightly here. So yeah, so the random function might be a little bit different. So very interestingly, what the variational autoencoders do, they don't learn the numbers, but they learn according to which random function do these numbers happen, do these numbers work. So, for example, let's say that we have a straight line in the middle, right? Let's say that we have a very high likelihood of the thing being there. Well, if we want to reconstruct from that high likelihood, well, we don't expect a straight line to be in an 8. We expect a straight line to be in a 1. So it makes a lot more sense in this case to treat those numbers as kind of like random numbers. You know, they could be a bit different, but they're still the same. And so this is exactly what the variational autoencoders do. They focus on a real line. So imagine that in this case, right, it goes from 1 to 100%. It's a probability of a certain digit having a straight line down the middle, right? Okay. So then you would expect the 1 to have a very high probability of doing it, right? Like, so it would have like between 80 and 97%, while the 8 would have between 0 and 20%. It's very low, right? So this is exactly what the variational autoencoders do. They try, instead of the numbers, instead of the exact point on this line, they try to find windows in which those features might fit. And this is what happens, right? So we have maybe feature 1 for something, and this feature 1 is very likely to be around 2.5. This feature, the second feature is likely to be around here, around here, around here. So if we want only to recognize maybe dogs in the pictures, right? And the dog features are very likely to be in this dimension, then if we have a number somewhere here, well, that's unlikely to be a dog, right? That's maybe a dog that's missing its tail, that we can't see a tail, you know, because we expect a tail to be here, but we don't have a tail, right? So we actually have a very low chance of a tail occurring, right? Okay, so, but then, well, you know, let's think about those tails, right? Let's say that we have a cat and it has a straight tail. Wait, it might be right down the middle, right? But the cat might have its tail slightly tilted, right? There's a very high probability that its tail is slightly tilted. It's not completely straight. But then there's a very low probability, as you can see in here, that its tail is like completely round, right? Its tail goes in a circle. So how can we represent that? Well, we could represent those features as random functions of these shapes. This is a normal distribution. In this case, for example, let's say that this is a tail. Then, well, you know, most tails are going to be somewhat straight, so they should be in here. This is also like a very high probability that if you tell this function to give you a random number, that this random number will be somewhere in here. So the tail will be somewhat straight, and a very low chance that the tail will be very curved. Yes, well, this is how it's basically defined. For example, if we have a digit 1, and digit 1 has to have a straight line in the middle, right? So, well, again, it is very likely to have a mostly straight line. Maybe it's less likely to have, to have a bit of a less straight line. Maybe it's a little bit curved. Maybe it's a little bit curved too much to the left, to the right. and then, you know, like a wiggly line, like a completely not straight one, but more of a circle, is very unlikely. So if we have a feature which falls directly into this proposition, then it is very likely to be a 1. And this is exactly what they do. They simply define, instead of defining those numbers, they define where those numbers come from and how likely are they to occur. And well, you might ask yourselves, well, why would we want to do that? Because actually the picture that you reconstruct is not the same picture that you input anymore. And that's true, but we then can treat images as having a probability of having some feature. So for example, in this case, the neural network has learned that having glasses on the face is actually one of the features. And if you increase the probability of having glasses on its head, then the person who previously did not have any glasses, upon reconstruction, will have glasses. So we can actually now learn that the glasses is a feature that has some likelihood of occurring, and if that likelihood is high, then we should draw a picture. And this is exactly what the thing does. And we have 5:48. We still have around 30 minutes. And I want, guys, for you to work on the demo, where you will use the convolutional networks to actually recognize the digits that we have talked about. I want you to look at the library PyTorch. There are some to-dos. There's some programming knowledge required. I want you to complete the demo by I took the working demo and I removed some code because I'm not very nice to you, and you have to try to, well, you can ask questions, but you have to maybe read something to try to, well, make this demo work again. Okay, this concludes my presentation.